Today we are learning Quicksort. Quicksort is very similar to an algorithm that we have covered before called Quickselect. There's no coincidence that they share very similar names. In fact, the way they work is fundamentally very similar to each other, in the sense that they both use an operation called partitioning, although what they achieve is very different. Quickselect is to select the k smallest number from an array, and Quicksort sorts the entire array. Now let's use an example to see how Quicksort actually works. For example, we have an array 5, 2, 1, 4, 3. And the idea of Quicksort is if we could put each of these numbers into its sorted position, then the entire array would be sorted, right? For example, if we put 5 into here, if we put 2 into here, if we put 1 in here, if we put 4 in here, if we put 3 in here, then the entire array is sorted, right? The question is, how do we put each number into its correct sorted position? The answer is partitioning, right? Remember that partitioning can put the partitioning pivot into its correct sorted position so that the left part of the array will always be smaller or equal to the partitioning pivot, and the right part of the array is always greater than the partitioning pivot. So how do we actually do that? Let's start with this example. 5, 2, 1, 4, and 3. If we use 3 as the partitioning pivot, then the array will become something like 3, 2, 1, 5, and 4. Okay, and 3 is in the correct sorted position already. And what we need to do is we need to take care of this part and this part. Let's look at the left part of the array first. Now we do very similar things. We look at the number 1 and we treat it as a partition pivot, and we partition the array such that everything that is on the left is smaller than 1, smaller or equal than 1, everything on the right is greater than 1. Then this part of the array will become 1, 2, right? And then we look at the right part of the array, and we use 4 as a partitioning pivot, and to partition this part of the array, then it will become 4, 5. And 3 is in here, so the entire array is sorted. And that is the idea of Quicksort. It is really simple, isn't it? Oh, I forgot to mention that for those of you who haven't learned Quickselect yet, or who haven't watched my last video on Quickselect yet, please go ahead and do so, because it is important to understand Quickselect before watching this video, because I'm not going to repeat all the very similar stuff that Quicksort and Quickselect shares. So make sure you understand Quickselect first. Okay, now let's go ahead and try to implement Quicksort on our own. Again, it is important that you can also reproduce this stuff yourself, because chances are you may need it in some interview. Okay. Let's first implement the partition function. So we'll choose the last number in the array as a pivot, and then we'll let an I pointer point to the first number in the array, and then we'll use a J pointer. We use a J pointer to iterate over all the numbers from left to right, up to right, but not including number on the right position. And then if we ever see that a number that we are iterating is smaller or equal than the pivot, what do? We want to swap that number with everything with the number on position I. I've covered this on our last video on Quickselect, so I'm not going to repeat things again and again. J I, and then also want to update I pointer. Okay, after we're done with it, we want to swap the right pointer with I pointer, and this completes the partition function. Now this is same old, so let's go to the Quicksort part. So what do we put in here? Let's do, remember that we want to find some number in the array and then partition the array based on it so that we can put this partitioning pivot into its correctly sorted position. So we are going to do some random partitioning on this array. Okay. And then in return, we get the index of the partitioning pivot. Okay, now what do? Then we look at, go back to our example. After we have put a pivot into a correct position, we want to look at the left half and the right half of the array. Let's look at the left half first. So we'll call Quickselect again, but this time we'll pass in the left half of the array, and we ask Quicksort to sort that part of the array. And then we will also ask Quicksort to sort the right half of the array. And we are almost done. But we still need a base case for Quicksort. So what if left is greater or equal to right? Like, for example, when we have reduced our array into just one number, maybe like number is 1, 2, 3, and then our left position now is 0, right position is also 0. We want to, this is when we have only one number left in the array. In this case, we want to return. Okay. Otherwise, we will partition the array and then we will recursively sort the left part of the array and recursively sort the right part of the array. And let's try to run this Quicksort program. It says partition is not defined. Okay, we should add a self prefix to it. Run again. Num is not defined. We have a lot of typos here. There we go. Num is not defined. Where is that? Oh, we have another one here. Okay, we have the input array is 9, 1, 3, 6, 4, 2, 10, 5, 8, 7. And after sorted, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. at time complexity of Quicksort. So remember that Quicksort, the way that Quicksort works is it first needs to do a partitioning. It needs to do a partitioning step on the entire array, which takes O(n) time, and this helps us place the partitioning pivot into its correct positions, and then we need to look at we need to sort the left half and the right half. Okay, and then we are recursively sorting the left half and the right half, right? And for the left half, we also need to do a partitioning. Imagine this half is having half of the original array. Then the partitioning will take O(n)/2. And same goes for the right half. It's also taking n/2 this much time to do the partitioning step. And if we need to further sort this part of the array, then we need to split them again into a smaller, even smaller array, and the same goes for the right half of the array. So we're doing this recursively, and imagine that if every time we are splitting the array into what is half of the original array size, then the height of this tree is going to be log 2n. Okay? And since in each level of this tree height, we are doing O(n) of work on partitioning. So it is always O(n) on each level. On the first level, we are partitioning on the entire array. It is O(n) for sure. And then we split them into two halves here, and we do partition on both of them. So it is also O(n) on the second level. First level, second level. And on the third level, imagine that every chunk of these, every little chunk of these array they have a size of n/4. Then if we add them up, it is also O(n) of work on the third level. Okay, so since we have log base 2n many levels in this recursive tree, and on each level we are doing a partitioning which takes n steps. So the time complexity of Quicksort is n log n. Now I know that I've made an assumption that in every split of an array, we are always able to split the two part of the array evenly, so that each part of the array has exactly n divided by 2 size. But that is not always true. Imagine that we could be like we have an array here, and then the partitioning pivot are lying here. So then we are splitting this array into, what was that? We are splitting this array into this half and this half. And then imagine that we need to do a recursive quicksort on this array. The recursion tree is going to have a much deeper, much higher depth than this array. And so overall, the height of the tree will be much longer, much higher than if we have split them evenly. But on average, Quicksort is still able to achieve time complexity of n log n. Again, average case runtime analysis of things like algorithms like Quicksort, Quickselect is very complicated. If you're interested, you can look it up yourself, but this is not going to show up in interview or something. Okay, I guess that is all for Quicksort. Hope you enjoy my explanation. See you in my next video.